This is question number 3 of the quantum mechanics chapter from Quantum Optics book by Mark Fox. Here it says, by using the definition in the first line of equation 3.32, prove the second. And I have written down equation number 3.32 over here for all of you. So this equation states that delta O squared is given by this particular integral psi star O cap minus expectation O whole squared psi integrated over the entire volume d cubed r. And this can be reduced to the second line, which is expectation of O cap squared, the operator O squared. So O squared is also another operator, which is operator O followed by another action of the same operator O minus expectation of O squared. So this is what we need to prove from starting from here. So starting from this line, we need to go to this line. And just for recap, for those of you who have missed, so O cap is an operator from the previous questions, if you remember the notation. So O cap is an operator and it represents measurement of an observable property. And this angular brackets, that denotes the expectation value, which basically means the average value. So average of all the results of the measurement value, that is denoted by this angular brackets. So this O is an operator. It basically means some measurement, and any measurement will give you some output value, and angular brackets denotes the average of those output values. So keeping that notation in mind, we need to solve this. And this delta O squared basically means variance. This is the variance, and variance is denoting the deviation about the mean. So if you look at this, the first line over here, you see this angular brackets, this denotes mean. So this is deviation about the mean, operator minus the mean. So this basically means deviation from the mean, and this gives us the uncertainty in our measurements. So uncertainty in our measurements, which is given by standard deviation, and standard deviation is just the square root of variance, which is just delta O. So this is a very important quantity. It gives us an idea of how much uncertainty we have in our measurements and how much the measurement values deviate or vary from the mean. That's why the name variance, and it basically shows how much the values of the output measurement vary or change from the mean. So this is what it is. Now we need to prove this definition over here. So let us start. So delta O squared, by definition, it is given in the first line. Now let us expand this squares. Let us use basic algebra. So this is O cap squared minus 2 expectation of O times O cap. So remember, expectation of O is the average value, which is just a number, and O cap is the operator. It will operate on any state, and then plus expectation squared. This is just opening this bracket over here. Now let us open up this integral. There are three terms over here, so let us write them down as three separate integrals. And O cap angular brackets, this is just the expectation value, so it comes out of the integral, and within the integral we have the following. Again, this is square of the expectation, it's just a number, so it comes out of the integral, and this is what we have within the integral. Now we will make use of the definition of expectation value from the previous problem. So in the previous problem, we saw the definition of expectation value given over here. Expectation of operator O cap is basically integral psi star O cap psi integrated over entire volume d cubed r. So using this definition of expectation, we can write down the following. So this first term is nothing but the expectation of O cap squared, the square of the operator. So operator acted on the operator again. The second integral is just the expectation of the operator O cap, and the third integral by the normalization condition is just 1. And normalization condition we saw earlier in the first problem over here, the orthonormality condition. So if the indices are same, let's say psi n star psi n, then this integral is equal to 1. So this normalization condition, using that we get the third term, third integral as 1. So it's just O cap squared, the expectation O cap squared. So this then we will just simplify. And simplification gives us the desired result. Finally, we have delta O squared equals expectation of O cap squared minus expectation of O cap squared. This is a very important result, and it will be used quite a lot when you want to find out the uncertainty in any given measurement. So this proves this definition for variance, and standard deviation, which gives us a measure of uncertainty in our measurements, is simply the square root of this variance. So if I were to write standard deviation is nothing but square root of expectation O cap squared minus expectation O cap squared. So this is standard deviation.